All right. So Fibonacci did not come up with the Fibonacci number sequence. He's famous for it, but evidently these numbers were around a long time before he came up with them. Fibonacci is known as the first important mathematician in Europe. One of the many things he did is came up with this sequence, and he adds 0 plus 1 and he gets 1, and then 1 plus 1 equals 2, and then 2 plus 1 equals 3, and then 3 plus 2 equals 5, and 5 plus 3 equals 8, and 8 plus 5 is 13, and then it's 21, 34, 55, 89, 144. What you're doing is you're adding the number that you just got to the previous number, and you get a larger number, and it's an exponential curve. But as this does this, this is the first 60 Fibonacci numbers here. And then we get to the second set. So this is 1. And this is the number 2,504,000,000, or so on and so forth. And the last digit's 1, as we had over here. This one, the very last digit's 1. This one, the very last digit's 2, just like you. So the very last digit of the first 60 to the next 60 to the 60 after that, the very last digit always is the same as the first group, 60. That's been known for a long time. What's been known for probably less time about the 9 digital rays, vortex math, Nikola Tesla saying if you only knew the significance of the 3, 6, and the 9, you would have the keys of the universe, and how this doubles halves and stuff like that. So I took what I knew about this vortex and how I knew to how I could take a number, divide it out into a note, or a note and divide it back into a number. There as 1 falls on digital root of 1, and then we get 2 falls on this ray, and then 3. Every one of these numbers, you can add them together. 21, 2 plus 1 is 3. 34, 3 plus 4 equals 7. 55, 5 plus 5 is 10. With 10, 1 plus 1 is 0. But also over here, we're going to get the same thing. In the very last digit of these numbers, you get to the 24th number, and then the 25th through the next, through 48. Again, the very last, the digital roots of the digital sums repeat in a 24 system over again. If you put them in a double circle, all of the notes that they are, there's opposites there. You can see here that this pattern kind of comes in and out and back in and out and in and out, so mirror image of one another. The system, the very last digit of the numbers for the first 60 to the next 60 to the next 60 to the next 60 are always broken down into the same groups of 24. The repeat, so we have a base 60, but we also have a base 24, and then it's 48, and then it's 72.
You're saying they always repeat?
Yes, these patterns in the math always. And so as I was figuring this out, and all of a sudden I realized that 60 is not where the lines lined up. If this orange line going off to the right, then left, then right, then left, and then it's pointing right here. The blue line goes to right, left, but this does not intersect here. Left, right, and left, and now they're going in opposite directions here, and then it's going right, left, not intersecting there, right, left, and then there's a 2. Now both of them are coming out this way. So I suspect that after the 240th, not only do these numbers, but the pattern will absolutely continue on forever.
Amazing.
Can't prove it. My computer doesn't go up that far. Wow. So I took the Fibonacci sequence and the first bunch of prime numbers, and the prime numbers that are Fibonacci numbers come off in the Fibonacci numbers that are prime numbers that land on C sharp or D flat come off in the first ray and in the fifth ray, always and only. The Fibonacci numbers that are prime numbers, where they intersect, only are on the digital root of A or on the digital root of 5, always only. Following these sets of math, following these sets of math for the other ones, hammer.
That's amazing.
Yeah.
That's absolutely amazing.
Yeah.
Wow.
And I don't know if anybody else knows this.
Wow.
This guy by the name of Marco Rodin discovers this vortex. He was a teenager. He was looking for God in numbers and found this. And stuff that I'd been doing for years fit perfectly into that.
Absolutely
and
awesome.
I had not a clue. The digital rays, the vortex, and the doubling and halving in frequencies, and so many of the stuff that I'd already done for years before that, all fit into all this.
Absolutely awesome.
Oh, so anyway,
Yes.
so now we have the digital ray of 5, and the note F is landing on here. So now there's a gap between here and here of 10, and then there's 14. 10 plus 14 equals 24, and then it's 10 and 14. This one here, when the numbers are landing on E flat or A, which is known as S, Y, there's a gap of 4 and then a gap of 20, a gap of 4, gap of 20. Sometimes these numbers are landing on the notes B flat, alias C sharp, and then there's a gap of 18 and 6, and 18 and 6, and 18 and 6, go on and on and on and on forever. 9, which is, then the gaps here is plus 12, plus 12, plus 12. In other words, kind of a mile marker here. And then these are going plus 1, plus 8, plus 8, plus 5 equals 24, and then it goes 2 plus 1 plus 8 plus 8 plus 5, and again another group of 24. This one does the same thing. These do the same thing as over here. Mirror images of one another.
Wow.
14 plus 10, 24. 14 plus 10, 24. 14 plus 10, 24. Goes on forever. A few years ago, during one of the snowstorms, I Googled, because it was interesting. I was out shoveling snow, and I Googled how much does the average snowflake weigh. The average snowflake weighed about 1/1,000,000th of a gram, and then they said in 1 cubic foot of snow there is about a billion snow crystals. So next time you're out shoveling, next winter, it's 1 billion, 2 billion, 3 billion.
That's amazing.
Starting here at 1. So we've got hundreds, thousands. I think we're right around in here. That's how many snowflakes, approximately, give or take a couple of snowflakes. Probably between the 54th, 50th. That's where approximately 1 billion would be. If we keep on going, because it's an exponential curve, by the time you get to the end of your driveway, this number here is so extremely large that I can't wrap my head around how big that number is. But you take these numbers and you add all of the digits down to a digital sum, and then the sums down to a digital root, and they're always going to come down to a number 1 through 9. Always. Any number in the universe does this. But then these patterns go 1, 1, 2, 4, 5, 8, 4, 3, 7, 1, 8, 9, 8, 8, 7, 6, 4, 1, 5, 6, 2, 8, 1, 9, and then it starts over again as it did over here. It's 1, 1, 2, 3, 5, 8, 4, to another group of 24, to another group of 24, to another group of 24, as it's going plus 60, plus 60.
Wow.
I don't know if anybody else knows this.
Wow.
I've called the colleges. I figured out Fibonacci numbers, figured out prime numbers, and who the hell are you?
Unbelievable.
Why don't you
Amazing.
pause? There's one more
Yes.
thing.
Okay, so yes.
So I was not exactly the best student at Gage Child at high school, but I did better in math classes than other classes. My 10th grade math teacher, his name was Dean Swift. I had to piss him off. I used to call him Dean. He didn't like that, so he used to call me Mud. So I'd get to school, I'd walk into his class and say, "Hey, Dean," and he'd point over, "Hey, Mud, how you doing?" And so this goes on all year. I'm calling him Dean. He's calling me Mud. And he'd be up at the blackboard, and I'd raise my hand and say, "Hey, Dean, I think the answer might be 43." And he'd point back to me, "Mud, you're right." And so it gets to be later on in the year, and he's explaining to us how to measure outside arc of circles and inside angles in triangles and stuff like that, and describing how to, once we've figured outside arc by angles which form triangles, and then how to figure out the inside angles of these triangles and stuff. So I raised my hand. I say, "Hey, Dean, is there any of your students going to actually use this math, like when we grow up, like when we get a job?" And he walks over to my desk and he points his finger in my face like this. He says, "Mud," he says, "shut up. There's 1 or 2, maybe 3 kids in my class going to actually use this math, but it's not going to be you. Well, why don't you shut up so that the kids who need it can actually use it?" 30 some odd years later, it was these mathematical angles and stuff that I was using to figure out music, to invent my chord teacher and the different chords and angles.
Absolutely amazing.
Yeah.
Absolutely amazing.